Okay. Okay, we can start, hopefully. Yeah, so welcome everyone. This is our first LLM seminar this term. So today we have Martin Schnee from Institute of Quantics, University of Sherbrooke. He's talking about this concentration-free kernel learning in the Rydberg-blockade. So Martin, please start.
Okay, thank you very much. So I'm very happy to be here and with all of you. Thank you for having me. So that's it. So I'm from Sherbrooke, Canada, the group of Stefanos Cortis. And today I will talk about some work of us. So it's called concentration-free kernel learning in the Rydberg-blockade. And it's related to a paper that we recently put on the archive. Okay, so let's start. I think I stop sharing. It's okay. It's okay. Okay. Start the recording.
Yes.
Okay. And okay, so here are my collaborators on this project. So a few postdoc, Ayana and Roya, the research professional, Victor, in our group that essentially cares about all the projects related to Rydberg atoms. And of course, Stefanos Cortis, my supervisor. Sure. So
Move your cursor down.
okay. Okay, so let me first give an overview, a quick overview. So I know that we are just after the lunch, so maybe we'll fall asleep in 5 minutes. So if you do, at least in 2 minutes, I can give you an overview of what it's about. So essentially, this talk is about quantum algorithms, and especially quantum algorithms for noisy devices that we have today. And so when you're thinking about designing quantum algorithms today, you face certain challenges. And among them, I'm interested in the three following challenges. First, we seek to address tasks that are of genuine practical utility. But we also want our algorithm to be hard to simulate classically. Otherwise, it's trivial. And of course, the hardware that we have today is very noisy. And so we have to be smart so that what we're proposing is implementable on today's quantum hardware so that we can really try stuff. Okay. And so I'm going to focus on a family of quantum algorithms that are hybrid quantum classical and that are called quantum kernel methods. And essentially the idea of this algorithm is to encode classical data that you want to classify into the very large Hilbert space of a quantum computer. So the thing is, so the important point is that with this family of algorithms, there is a problem, which is the following. When you try to scale up the size of your quantum computer, essentially the output of the algorithm, what you measure, all these outputs will become indistinguishable very quickly. So it means that you won't be able to use in practice this kind of algorithm. And this work is about finding a solution to this problem. And so building a quantum kernel that doesn't have this exponential concentration problem. And for that, our solution is inspired by physics and by a phenomenon called weak ergodicity-breaking that some of you know very well here. And furthermore, this phenomenon naturally arises in Rydberg-blockaded quantum computers. So that was for the overview. So let me start with some motivations for doing quantum, so machine learning, quantum kernel learning is a subpart. So what does it mean? So again, so first, what is maybe a machine learning? So so in today's world, essentially, the data is absolutely everywhere. And we are very interested in being able to process very large amounts of data. And it turns out that classical machine learning techniques do a very great job. And so it's, when you say classical machine learning techniques, it in fact covers a huge variety of algorithms. And but the point is that this algorithm want to be able to make predictions about unseen data from training on previous data. So these are sort of a black box algorithm that are not programmed specifically for solving a task, contrary to other kinds of algorithms. And so essentially, what is interesting for quantum computing is that machine learning provides very good example of hard problems. So in quantum computing, we are interested in finding hard problems because we would like, ideally, that our quantum computer used to solve these problems. And there is like a reasonable hope that the quantum computer may provide an advantage on this problem. So of course, we have to be cautious because there is a lot of hype behind all these words, quantum machine learning. So this is cautious optimism here. But so if you read the headlines, of course, usually cautious is sort of thrown away. We try to be cautious in this talk. Okay, so what about quantum machine learning? So as you may know, there have been lots of progress recently on building small quantum computers. Unfortunately, these quantum computers that we have right now are extremely noisy. They are limited in terms of the number of qubits that is available, in terms of the depth of the circuit that you can run on it, and in terms of the number of measurements that you can perform. So here, I've put an example of quantum computers based on atoms, neutral atoms, that you can arrange in 1, 2, and 3D. But there are, of course, many kinds of platforms. And so essentially, the problem with this limited device is that we would like to run algorithms on them, but when you go from one platform to the other, one algorithm that was really simple may have to be translated into the natural language of this platform, the natural gate set. And this can really increase the depth of the algorithm. And on top of all the limitations that I talked about just before. And so one possible strategy is to really start from the hardware, start from what you can naturally do on this kind of platforms, and try to design quantum algorithms that are really naturally implementable machines. So essentially for us, quantum machine learning will refer to parameterized quantum circuits. So what I mean by that is that you have a platform, so for example, neutral atom or superconducting qubits, and you know that with this platform, you're able to naturally realize certain kinds of gates more naturally than others. And the idea is that you will start from these gates or the unitary that you can do, and you parameterize them. So these gates depend on some real parameters, and essentially you will use these parameters as a way to input classical data that you want to process in the quantum algorithm. So the circuit that you get out of that, the algorithm that you can make can take different forms. So you have things that, for example, you have alternating layers of different kinds of circuits. You can have mid-circuit measurements. But essentially, the kind of circuit we're going to focus on in this talk is this kind of circuit where you have a unitary evolution, which is parameterized by like some x parameter. You can think about the x as some data point in the vector space, and followed by the inverse unitary evolution parameterized by another point. And at the end, you perform simple measurement in the computational matrix. So it's a very simple setup. And the platform we are interested in are Rydberg-blockaded arrays. Okay, so now let me give you an idea of the family of algorithms we're interested in. So this is called kernel methods. This family of algorithms comes from like classical techniques, and the goal essentially is to identify different classes in a large data set. So here I represented a data set of pink and green points in some space. And the idea is that we would like to separate the pink from the green data. So how do we do that? So the idea is that we would like to devise a function that does this job, so that is able to assign to each point in the data set the right class. And in fact, so we won't be able to build this ideal function, but we'll seek to construct the best possible approximation of this function. So how do we do that? So the starting hypothesis is essentially that this function that we want to build is able to do the job only from the knowledge of the position. So here I'm being vague, but the position of each data point relative to the others. So if we can compute the similarity measure for each point relative to all the other, then knowing only this, we can do some optimization to find this approximate classifying function. So here is what this approximate classifying function can look like, and you see that you have two objects inside. So the kappa is this similarity measure that we call the kernel. So that we'll have to compute that first. And then we can run an optimization algorithm to find the optimal weights so that we get the classifying function that is the closest to the ideal. So essentially, it's a two-step process. But the question is, what is a good similarity measure? So it's a crucial point here. So the idea is that to help classify the data, we want a similarity measure that takes this data and projects it into a very high dimensional space, because then it will be much easier to classify the data, essentially to find hyperplanes that are able to separate the different classes. The thing is, we don't want to explicitly compute this mapping to the high dimensional space, because it can be very computationally intensive. And so we want to do that implicitly. So what we want to compute essentially is to, since we want the similarity measure between pairs of points, since these similarity measures take the form of inner products, we just want to be able to compute these inner products in the high dimensional space without having to compute the mapping itself. And then it's just a two-step process. You build your kernel matrix, which is this implicit projection, and then you use this data and put it in an optimizer of a loss function. And there, the good thing is that you have guarantees that this optimization step will converge towards the ideal weights, essentially. Yeah.
How do you import your information in the computer? Do you not have to do the computer the positions and the color in the first place? Or
So the
or
idea,
is the idea that you then can put the point anywhere and it will tell you whether it's color it tells?
so the idea is that this data, so you can imagine that as the training data, and you want to build this classifying function. So the goal is to have this so that then you can use this function on unseen data, on new data. So you will use training data, and on this training data, you want to first compute the similarity measure, optimize the weight so that you build your tool, your classifying tool. Sure. Yeah.
This time, so can you just explain in this time is simply the data in the space that you want to, and the X is the data space that version of in bullet.
No, here it's much simpler than that. It's just I called X this specific point and Xi all the others. So I'm just compute for each point. I look at the similarity with all other points paired. So essentially, this object, in fact, looks like a matrix, because for each point you look at the similarity with all the others. So you could put all this information into a matrix. Okay, and so the idea here is that, so the second step is somewhat easy because you have guaranteed convergence for optimal weights. And the first part could be done on a quantum computer. Why that? So for that, so this is the idea of quantum kernel learning. So extending this classical technique to the quantum realm. And so why do we think it's a good idea? So the motivation comes from a great similarity between the framework of quantum kernel methods, where you have a data space, you have this feature space, which is the high dimensional space, and you don't want to compute explicitly the mapping, you just want to access information about what is happening in this space from the kernel, the similarity, pairwise similarity measure. And in quantum computing, in some ways, we do the same thing. We could have quantum states that depend on real parameters. So in nature, these parameters could be the parameters of in your Hamiltonian, field, all that. But for sure, the quantum state, for example, at the end of a unitary evolution, will depend on these real parameters. And through the measurement, you cannot access the exact wave function. what you can access are things like fidelities, for example, or expectation value. So there is a real similarity in that matter. And so concretely, it means that we're going to encode each data point into quantum states via a unitary evolution. So we start from an initial state, size 0, and we choose our parameterized unitary, and we input the data point into the unitary. And then we do that for another point, x prime, and what we want to measure at the end is a fidelity between these two quantum states. So the circuit looks indeed like this. We have size 0, encode the point x, and encode x prime in the reversed evolution, and measure the occurrence of size 0. Okay, so now we are coming to the problem of this kind of methods. So these quantum kernel methods suffer a problem called exponential concentration. So what does this mean? So remember that our quantum kernel is in fact a fidelity that we want to measure. And what we will get, so we will do like many experiments so that we can estimate this fidelity for all the pairs of points. And this fidelity essentially depends on the number of times you measure size 0 over the total number of measurements. It's a statistical quantity. And what we really want is to be able to distinguish the values for each pair of points, to have really meaningful information about the original classical data. So that's it. We want the estimation of this quantity to be the most accurate possible. And the problem is that when you increase the size of the quantum computer, what happens in general is that the value that you output are really concentrated around a single constant value, so that they will become indistinguishable. So here I represented the kernel matrix. Just to be very concrete, we are looking, so points on the diagonal correspond to this the fidelity between the same point, prime equals x, and all the other diagonal points correspond to the similarity between different points. So we're interested mostly in different points, and we look at the mean and the variance of these values. And if we see that they tend to concentrate around the mean exponentially fast as we increase the system size, and this mean becomes very small, very close to 0, then it means that it's impossible to use the output in our algorithm. So the open question is, in this field, can we find a quantum kernel that does not exponentially concentrate? And of course, we want this to be still hard to simulate. Otherwise, the kernel is trivial. And I mean, it's a first thing. Of course, we would like also to be able, for example, to tackle complex data that are intractable with classical techniques, but let's say it's the second step. At least we want this to be hard to solve. Okay, so how do we do this? Other question at this point?
Yeah, I have a question. So like, I mean, the issue here isn't that the unitary you're applying is really handling, right? It's just that any two states are orthogonal if the system gets bigger, right? Is that the actual? Like, the problem is that like if you have any two wave functions in an infinite system, they're either the same or orthogonal, right?
So I'm not sure to understand. Here, the,
So like, so the problem is like for any, like x's that are different, you have to say like exponentially small signal, right? Like we kind of,
yeah,
and like, but that's not really because of any choice of the unitary, that's just because if you have any two states that aren't the same in a sufficiently big system that.
so there can be many sources to why you have exponential concentration. So for example, if you imagine that the unitary you use is something like chaotic. In some way, the original information that you inputted through the parameters will become completely diluted in the exponential Hilbert space. So when you try to measure the fidelity, meaning the overlap with the initial state, it's necessarily extremely small.
Yeah, I think what Andrew was trying to say that if we have two states, right, whose overlap is, let's say, 1 minus epsilon.
Yeah.
And if we blow up the number of qubits, 1 minus epsilon to the power n
Yeah.
always goes to 0, right? Because n becomes large. So the overlap for a very large number of qubits is either 1 or it just goes away to 0. There's kind of not really anything in between.
So that's so I mean, I will show that we find something else, but it depends a lot on the kind of observable that you're measuring. So for example, it's really true what you say for a global observable, but you could, instead of measuring this global fidelity, you could measure more local observables. It also exists, and then you're more likely
to replace the overlap with some expectation value of something else.
Yeah.
Right.
Observable.
Yeah,
Local
that would have a well-defined limits.
Yeah, absolutely. So, but for sure, in the case of a global observable like the fidelity, it seems unlikely that you will have like a solution. At least in general, that you will have guarantees. So that's where the physical phenomenon of ergodicity-breaking makes sense. Yes.
It's not from the scale, but it's a bit, sorry if I overlooked something, but if all the points are completely random, what color they are having, then you cannot, as soon as there's probability involved, you cannot predict there's probably the kernel changes, or is there even a kernel?
So if your data is random, so
If the color of the dot is blue or green,
so
then blue.
so this okay. So here you're talking about random classes, and a lot of many classes. So so yes, if so then I'm not sure if you had like I don't know 100 points and 100 different classes, maybe it gets complicated. But the goal here is more to have randomly placed points in the space, but there are only 2 or 3 classes, for example.
But if you have randomly placed points, they are either red and green, but whether it's red or green is random.
That's fine.
That's fine. Yeah, that's fine.
Because the intuition is that like when you do this mapping, you're finding this hyperplane in this high space that really is like, there is like a feature you're distinguishing, right? Okay. So in some sense it would fail if like there isn't any, you'd never get like a converging result, I guess, if it really was like completely random. So there's no like feature to learn, right?
In fact, there are, I think, pretty sure there are theorems that show that if the dimension is high enough, you will always be able to find a hyperplane.
But then every time you add a point, your hyperplane will change.
Yes, absolutely. It doesn't mean that you have a guaranteed convergence that you find the optimal hyperplane.
But you still find this, you still get a solution.
Yeah. Yes, absolutely. That's the main advantage of this kind of method, the two others. Okay, so the question is, how do we find this kernel, quantum kernel that doesn't exponentially concentrate? So here, our secret ingredient is to use many-body dynamics in Rydberg atoms quantum computers. So these are Rydberg atoms. So just a quick recap on Rydberg atoms quantum computers or simulators. Essentially, you have an array of neutral atoms that are trapped in optical tweezers, in lasers. And you can have, so now we are able to trap these atoms in space in 1D, 2D, or 3D. And each of these atoms are Rydberg atoms. So it means that the outer electron can be either in this ground state or extremely excited. And so these atoms act as qubits. They have a 0 and a 1 state, and they can oscillate between the two. And so this is about the local control of these qubits, but you can use this Rydberg state to make them interact also. And so here the idea is that when the electron is in this very excited state, essentially these atoms look like electric dipoles because you have a minus charge and the rest is like an effective positive charge. And so you have a dipole-dipole interaction, which is effectively van der Waals force. So it looks like this. So here the operators N, Ni, and Nj mean that this interaction is on when the two atoms are in the Rydberg state. And the strength of this interaction decreases really quickly with the distance between atoms. But it depends extremely strongly with the Rydberg level, so to the 11th power. So it means that it's really easy to engineer very strong interactions. And so in the end, you get an Hamiltonian that looks like this. So you have the local Rabi term. You have the interactions between any pair of atoms. And on top of that, you can have a detuning between the energy gap of each atom and the exciting laser. This is the Rabi term, the van der Waals interaction, and this is the detuning. And so as I was saying, it's really easy to reach the very strong interaction regime. So this is the regime where the interaction between the nearest neighbors is much stronger than all the other energy scales. And this regime is called the Rydberg-blockade. And so in this Rydberg-blockade regime, you have a very interesting kind of dynamics. Essentially, when you look at two neighboring atoms, the configuration where they are both excited is forbidden. So you can only transfer from these configurations. And what this means is that if you start from a simple product state, which fulfill these constraints, so for example, this product state, where no atom is excited, so you don't have at all this doubly excited pattern, it means that the dynamics will be trapped in a constrained Hilbert space. That's the first thing. This is related to something called fragmentation of the Hilbert space. That's it. So you're trapped in a subspace that is still exponentially large with the size of the system. The other interesting consequence is that for certain initial states, for example, the antiferromagnetic state, you will have very interesting kinds of many-body dynamics. So if you start from this or other well-chosen initial state, what you can see is that these initial states will revive periodically for very, very long times. So they sort of resist thermalization in some way, and this is due to the presence of special eigenstates in the energy spectrum that are called many-body scars and that are very low at time. So in fact, we're going to use this kind of special dynamics that resist mixing as a resource to build our quantum kernel. So in practice, here is how it looks like. So you remember that our kernel looks like this. And so the idea is to use the Rydberg Hamiltonian in the Rydberg blockade to generate this U. And we will use the detuning perturbation to encode the data point X. Okay, so we encode V via the detuning perturbation. We start with this antiferromagnetic initial state as this special dynamics. And for the evolution time, we will choose like a fixed evolution time that hits exactly the revival time. So we can choose to go up to the first or the second or the third revival, for example. But that's it. We choose to hit precisely a revival. So what this means is that when you do U and then U dagger, what will happen, for example, if you choose 2 revivals, is that you do U, which is slightly perturbed. So it will essentially change the height of this revival. And then you evolve back, but with a slightly different perturbation. So you will have something that resembles going backwards, but not exactly. So you won't go backward to 1, except if x prime equals x. You will go back to a probability that is really high, but not as low, equal to 1. Yeah.
So what is the intuition for choosing delta to encode?
So, okay, so here, as I'm coming to this. So the idea is that as we were talking a few minutes ago, since we are looking at a global property, the fidelity, a global observable, there is a high risk that we cannot really estimate this quantity when we increase the size of the Hilbert space. But if we use the fact that built-in we have a high fidelity, and we use an encoding perturbation that doesn't change this feature, then it means that the end fidelity, the kernel, will stay high. And so we will need only a polynomial number of measurements to estimate this quantity. So the fact that we have revivals here is very important. So there are like several works that show that this kind of perturbation doesn't really change the revival behavior here. So that's why we use this perturbation in particular. And so this hand-wavy intuition is confirmed in part by a time model. So we can approximate this kind of dynamics by the precession of a very large spin. So this is only an approximate time model, so it captures the oscillation behavior, the oscillatory behavior with the period, but it doesn't capture the fact that it decreases over time. But with this time model, we can analytically compute what should be the behavior of the kernel itself. So this forward, backward dynamics. So at least it gives something that is analytically trackable. So you will see that then I will compare numerics with the whole system versus the behavior that we predict with this time model. Okay, so let's come to the result. Okay, so just a reminder, what we want to show is that we don't have, for the mean and the variance of the kernel value, we don't have this exponential concentration as we increase the system. Okay, so what we're going to do is to test this on a random data set. So we generate random data points in some space to which we attribute a class, so 2 different classes, for example, and we compute these quantities. Okay, so the first one is the mean. So in fact, we plotted 1 minus the mean, and we plotted it for different revival times, so longer evolutions, for example, and also different, so what we call number of feature just means that the data points live in, it's just the dimension of the data. So the data points are vectors, and here they can be either 1, 2, 4, or 8 dimensions. That's it. Okay, so and here, what we want to see is not this. So we plot in a log-log scale with the system size, and we compare it to first the analytical toy model. So what the analytical toy model predicts is this linear behavior. And in fact, we see that it's roughly what we find. So we don't find exactly the same kind of slope, but because the toy model doesn't take into account the fact that the revival tend to dampen with time, we are not surprised. In fact, what the toy model predicts is that exactly at the revival, we shouldn't be able to use it with perfect revivals. But since our revivals aren't perfect, in fact, we can. And we find behavior that is qualitatively the same, but the slope is just not exactly the same. But we are happy because this obviously doesn't concentrate toward an exponentially small value. Then we plot the variance for the same data. So where here we also have a comparison with the toy model where the behavior should be quadratic. And we see this qualitatively the same kind of behavior. So the slope is a bit different, especially as we go higher in the evolution time. But again, we do not exponentially concentrate. Okay. So now that we have confirmed that our kernel built from Rydberg atoms does not have this problem of exponential concentration, of course, we want to know whether it's able to classify real-world data, of course, because I mean, this is the point of this kind of algorithms. So for that, we test the classification performances on a real-world data set called the iris data set. So it's a data set of flowers. So each point in this data set, you have 150 points. Each point is 4-dimensional, and you have 3 different classes, so 3 species of flowers. And here we plot the accuracy. So we train the kernel-based model using simulating this quantum evolution. And then we use it on unseen data. So basically, we split this data set into data for training and then unseen data. And what we see is that we have rather good classification performances. So we are good in this field means that you're roughly above 75%. So here we see that we hit roughly 90%. And so to be fair, we've compared it to classical method. So you see that classical method still beats the our quantum kernel. But here, the idea is more to show that we are able to classify at least, and but we haven't tried to find the best tuning of our quantum kernel so that we optimize the performances.
The chance that you ever beat the classical?
I don't exactly know. This will necessitate a lot of work, that's for sure. Because, for example, so that's okay. That's one of the main questions for us. There are sort of two main questions for us. The first is this question: what is the underlying resources that allows this quantum kernel to be able to do this? And the other is to find what kind of data it's best suited for. Because here we've used this data set because it's sort of the simplest data set you can, real-life data set you can imagine. But the thing is, for example, the Hilbert space where we are trapped has some structure, and maybe certain kinds of classical data would be best suited for the structure of the Hilbert space. But this we'll have to explore, especially with the help of machine learning experts. Yeah, for example, or maybe we could, if we're able to make a link between this construction, the way we construct the kernel, and for example, quantum information resource theories or something like that, maybe we could gain some intuition about how to tune exactly this kernel so that we optimize its performance.
Are you looking for some kind of the classical kernel to try to get there faster, or do you have some quantum hyperplanes that you could with?
I'm not sure to understand the question.
To distinguish these species, if you work in a Hilbert space, you can probably separate states in a different way than we do classically.
Yes, but the theory for this is not very clear. So so I don't have a precise intuition of what kind of Hilbert space I'm constructing.
So at the moment, you're trying to emulate the classical solution on the quantum.
So for the moment,
The data is classical, and it's just using this quantum.
yes.
When there seems to be some interesting interplay between system size and when you stick to the first revival, because it seems to be getting better and better as increasing system size.
Yeah.
Whereas the other revivals are kind of probably too far off, but there's not much you can do. But I guess it would be interesting to know how far the first revival will improve, right? If you keep increasing the number of qubits.
Yes,
Maybe it will reach or beat class.
absolutely. Yeah. That's it. There are many parameters with which you can play here. So is it, for example, if the resource underlying this is entanglement, maybe it's worth going very far in the number of revivals. But maybe what is interesting is
No, but this really shows that there's no point in going further in revivals, right? Because 3 is completely flat, right? It's nothing weird changes.
yeah.
So 2 and 3, they've already saturated, but the first one is interesting because it keeps going up.
Absolutely. But for example, I mean, this is okay. This is true for this specific data point with which is in fact small compared to other real life data sets. So we have only like a 4-dimensional data, all that. But for example, the next step is clearly on the machine learning side to test that with increasing number of features to see if maybe there is, for example, a link between the encoding time that you choose and the number of features, so the dimensionality of the data that you want to encode. Maybe encoding higher dimensional data requires more time. Important step.
So more parameters in it. Like it could be that all you have is delta. That maybe that's just not giving. It's still probably only parameterizing some plane in your open space, right? Whereas you if you had like 2 parameters in your input and your output,
Yeah. So
right.
So here, for example, to encode 4-dimensional data, so you have vector with 4 numbers. Essentially, what we do are layers of evolution, each of them with a delta.
The different delta.
With a different delta.
Okay.
But maybe it would be better we choose this because, I mean, there were no, there was not like a good argument to choose like another method, but maybe we should encode the delta more locally. So here there is really a lot of work on optimizing this protocol and understanding how to optimize it.
Sorry, Martin. I have a quick question.
Data into a much smaller system because you have the quantum degrees of freedom, or you use a big system.
So what you're referring to is something close to reservoir computing in some way. So where you sort of connect the qubits where you are encoding the classical data to sort of a bus, and you use the fact that you have access to a high-dimensional bus to sort of improve your algorithm. So this is the setting is a little bit different. But
then you could get the advantage of your quantum system giving you many dimensions much more quickly. Then that might be a resource for.
yeah, for sure. So if you think about measuring local observables, the risk in some sense is that your protocol becomes easier to simulate, and we want something that is hard to simulate. So that's why we're focused on measuring global observables again, where we know that exponential techniques, which are the best numerical methods of these kind of dynamics, are still limited. So all these simulations are key to so that's the end of my presentation. So to summarize, we've proposed a way of building a quantum kernel that is based on the weak ergodicity-breaking phenomenon, and we find that it seems that we solve this exponential concentration problem, and the main advantage being that it's still hard to simulate classically, but it's naturally implementable on neutral atom quantum computers. And in terms of open problems, so the next step are, so we talked a bit about these. There is what is the resource behind the performance of the proposed kernel? So there are many things happening in this kind of dynamics: quantum scars, fragmentation, the fact that we specifically hit high fidelity revivals. So what is happening? So clearly there are easy things we can think about checking. So for example, if instead of using the antiferromagnetic state, we use the completely polarized state, the zero state, what happens? So we're investigating these, but clearly there is a lot of work to do here. And on the machine learning side, there is also a lot of work on the kind of data we are processing. And of course, we would like to go to 2D, because in 2D, you're sure that in terms of classical simulability, very quickly it becomes very complicated. So that's all for me. Thank you very much.